Let's consider a simple file system where we have one video, a folder with a text file, and a link to a file system of somebody else. First, we create a descriptor for the video, which is a JSON file containing an array of hashes describing how to put the fragments together. Once the application produces such a descriptor, it immediately splits it into fragments, like a regular file. Because the descriptor is a regular file, so it can be stored in a distributed data storage as well. Therefore, a file descriptor is actually represented by 4 hashes. The folder descriptor is somewhat more complex. A folder can contain files, subfolders, or links to other file systems. Large files, like the Simpsons video, are represented by a reference to the file descriptor from the previous slide. Smaller files can be stored directly in the folder in base64 encoding. And foreign file system linked here as a subfolder redirects the user to a file system of somebody else. The folder descriptor has the most complex structure, but it is still relatively easy to understand. Once JSON descriptor of the folder is created, it is multidimensionalized and stored in a data storage. Finally, we have the file system descriptor. This contains the signature key, the communication key. Those are so-called golden keys. Their private part is known only to the author of the file system, and the public part is a unique identification of the file system. There is also a root folder update links and root folder tachyons, which are very useful when publishing information about new file system, and they can be used for hidden communication among users. We will talk about update links and tachyons later in this tutorial, but now let's return to the topic of signature and communication keys. I think we live in an era when usable quantum computers are literally almost here. Therefore, we should always use quantum-resistant cryptography at least for our golden keys. That is why the MLDSA and MLChem were chosen as a default encryption algorithms. Finally, as always, we split the file system descriptor and store it in the distributed data storage. And here is a diagram of all 3 objects and their relationship that makes up the file system. Now let's discuss how to upload and download fragments into our peer-to-peer network. Downloading the fragments is very easy and straightforward. Uploading is a bit more complicated because, as mentioned earlier, each user can share only fragments of a certain color, which depends on a hash of the public IP address of the user. So, if the user wants to share data with the rest of the world, they have to exchange some of their fragments which are not compatible with the color of their IP address with other users. For example, if your IP address is red, meaning the hash of your public IP address starts in binary code with 00, then you, and I mean the application responsible to store data in data storage, must go to the Fragments marketplace and exchange green, blue, and white fragments with other users. The exchange can happen directly or through the Tor network. Most importantly, this exchange is not widely broadcasted. It is rather limited to a tiny circle of so-called friends, and the software makes sure that it is impossible to detect who produced the fragment and when exactly it was produced. After the fragments are exchanged, the software waits a while, typically a few minutes, and registers hashes of those fragments into a distributed hash table. Again, this can be done directly or indirectly using the Tor network. As mentioned before, downloading and resharing is fairly simple and straightforward. Anyone with a file system descriptor can download any fragment of any color from the distributed data storage and combine them together to fuse, or assemble if you wish, the file system, and after that individual files of the file system. There are 3 major download strategies. The most common and most paranoid strategy is the strict mode, where the user shares only what they downloaded and only fragments of the same color as their IP address. The standard mode allows automatic exchange and sharing of fragments from friendly peers. Obviously, those fragments must have a proper color. Then there is a naive mode, which allows anybody to push fragments of a specific color to the user's cache. Those will then be shared automatically. But almost nobody uses naive mode. Standard mode is the way to go. There is one more thing worth mentioning. The so-called quo-pro-quit model, which effectively eliminates the existence of parasites. Parasites are those users who do not contribute to the network. They only download files but never redistribute them. The quo-pro-quit mechanism makes sure that everybody contributes to the network. For example, if Ron wants to download data from Richard, then Richard can return a completely different fragment back to Ron and order Ron to forward the fragment to Alice, Bob, and George. Only and only then will Ron get the fragment he originally requested. Of course, this behavior is triggered in situations when there is a lot of interest in a particular data to expedite fragment distribution, and occasionally as a test of obedience. Well, now we shall perform an exercise. Let's switch aside and for a moment pretend that we are law enforcement and we want to break this network down and arrest as many people as we can. We will quickly find out that in almost all cases it is impossible, but that is a topic for the next video.